Hello and welcome back to Educator.com and welcome back to physical chemistry. So in the previous couple of lessons we talked about changes in energy and state, and we did them under constant volume. Now we're going to hold something else constant. We're going to see what happens to the energy of the system when we hold the pressure constant. So let's dive right on in. Okay, now most lab procedures are conducted under constant pressure conditions. So most lab procedures are carried out under conditions of constant pressure. It's just a lot easier that way. A lot of the experiments that you do, you're doing it on a bench top. You have the constant pressure as the atmospheric pressure. The reaction runs, the system changes pressure, it accommodates this pressure inside the system is pretty much going to be the same as the pressure outside. It's always in equilibrium with that. So constant pressure conditions are very, very simple experimentally. So most lab procedures are carried out under constant pressure conditions, under constant P conditions, which is atmospheric pressure. So the pressure, which happens to be the pressure of the system, happens to equal the external pressure. That's all that means. Now, let's start with, so again, we're playing with the mathematics. That's what we're doing. We're hoping that manipulating the mathematical expressions will show us something, will give us something that we recognize. Maybe we'll see something, maybe we can move this around, move that around. That's all we're doing. So let's start with du is equal to dq minus dw. Well, dw is equal to P external times dv. So du is equal to dq, and again, we're working under constant pressure conditions, minus P dv. Okay, well, since P is constant, again, this is just the first law of thermodynamics, that's it, is constant. Upon integrating this, upon integration, we get the following. So we get integral from an initial state to a final state of du equals integration from an initial to a final state of dq sub p minus p times the integral from initial state of dv. Again, pressure is constant. Right? Pressure is constant. We can pull it out from the integral. So we end up getting the following. This is going to be, instead of using the delta symbol, I'm going to actually write it out explicitly. So this, u is a state function, so this becomes u2 minus u1. This is a path function, so it just becomes q sub p, the heat withdrawn from a system at constant pressure. And this is going to be minus p times, well, volume is a state function, so this is going to be V2 minus V1. When I distribute this and move it over to the left, I get the following. I get U2 minus U1 plus P V2 minus P V1 is equal to QP. So far, so good. I'm going to rearrange this and put the u's and p's together, the 2's together. So I get u2 plus pv2 minus u1 plus pv1, right? This is a minus u1, that's this one, and minus that, that's this one, is equal to QP. Well, since P is equal to P1 is equal to P2, the pressure is constant, so it doesn't matter. The initial pressure is the same as the final pressure, so we can just call it, it's just P. That's what P is. So we can go ahead and put wherever we see a P that's associated with a 2, we can put the P2. And wherever there's a P associated with the subscript 1, we can go ahead and put 1. So we get the following. We get U2 plus P2V2 minus U1, not U2. I always do that. U1 plus P1V1 equals QP. Okay. U is a state function. We know that. Is a state function. Pressure is a state function. Volume is a state function. So P is a state function. Volume is a state function. Therefore, the sum of the state function, the product state function, is a state function. So this whole thing and this whole thing, they are state functions. So this U plus PV is a state function. We're going to